Everybody to the afternoon session. Everybody has 20 minutes for the presentation. When I will do this sign, it means that you have still 2 minutes left. So please try to go faster towards the conclusion, because I will stop you at the end of the 20 minutes and then take maximum 10 minutes for questions. Whenever you're ready, please start.
I would like to start expressing my biggest thanks to the process, Dr. Samini, Dr. Villa, and Dr. Ziki. I would like to start my presentation by expressing my deepest thanks to Dr. Villa, Dr. Zuki, and Dr. Samini. Today I'm pleased to present my master's thesis on design of container mechanics for trash collection and quadruped robots. I will start with a short introduction to show the importance of the work. Then I will discuss the current robotic solutions and their limitations. I will discuss some background, and then I will start my project by defining the conceptual designs, down selection, simulations, mechanical design, manufacturing, and assembly. I will discuss the features, and at the end I will show the test and validation and conclusion. An alarming amount of 2 billion tons of the waste is producing every year by human, and a huge amount of it is not collected well. And this global challenge related on human health by spreading the disease. It's because there's some animals, and also it will make the tourist places less attractive. Currently, these trash are collected manually with field because safety risk for the laborers, it is very expensive, and also the trash in the hard-to-reach areas is not collected well. Currently, there are some robotic systems to help us for this task. That, as you can see, for instance, the first one is using a wheeled platform and also a special mechanism mounted on it to collect the trash and store it. It's a very good idea to integrate the robotic arm with the mobile platform that you can see in the third and second one. Then, for instance, the second one, you can see the arm one is mounted in front and the container in the back of the mobile robots. And similar approach is deployed for the third one, that is deployed, it is developed by IIT in 2020. But why the current existing robots are not sufficient? Why we still need new robotic systems? The trash, the current solutions are using wheeled robots that will get stuck in the hard-to-reach areas or on many trains. That's why we are introducing a great solution, which is linked robots, which with higher locomotion capability. For instance, as you can see in the first and second videos, this is the high-Q real robots developed by Yanmar Reflex System at IIT, and third one, ETH Studios Animal, that it is clear how effective they can be for trash collection. But imagine we have the linked robot. How this robot can collect the trash? We still need a robotic systems mechanism in order to do all the steps from detection, collection, storage, and unloading automatically without the help of human. Also in here, there is a good idea to integrate the arm robotics with the linked robot this time. And as you can see, there is a clear need for a robotic mechanism that can be mounted on the robot or the container in order to perform all the steps automatically. Therefore, we define our background of the project by defining 3 main subsystems. The first one is Unity a linear linked robot. Second one is Unity Z1 arm robot. And the third one, which is we discussed in this thesis, is the custom designed container mechanism. Actually, the cycle is planned in a way that the alien robots works in the work environment and they take the trash with the mounted camera, and then the arm robots grasp it, drop it in the container, and then the container is full, and then the robot navigates to the station to unload the...
Sorry. I think you are mute on Teams. Can you please check? Because Dr. Semini is telling me that...
Can you stop the time? Sorry.
It's okay.
Now it's fine.
No, did you
It's fine now.
No, did you go? Can you show me Teams? Okay. He says okay.
It's fine. Okay, thanks.
He's happy now. So it works. We'll just move it, it's better, yes.
Okay. So the container that we are going to develop requires to have some specifications, such as it should have the feature for autonomous trash unloading without any extra actuator. It should be lightweight to adapt with the Allego linked robot. It should be under 3 kg, considering the weight of the arm and everything. It should have a seamless interaction with the quadruped robot and also the arm robotic. And it should have enough capacity for the trash. Therefore, we started the project by brainstorming about the possible solutions. That at first I designed my ideas on the paper, and then this brainstorming led to 5 different conceptual designs that each one has its own advantages and disadvantages. Then we continued the process of down selecting. Starting with the first conceptual design, this is the most simple the mechanism that comes to mind. But as you can see, the hook is that it is simple, but it has very high gripper motion, which probably is not out of the robotic arm workspace. And also it is very unstable because it's attached from on one side. Then we move to the second conceptual design that is still simple. You can see that it has 2 main bodies, that one is the internal basket and one external body, and the handle is mounted on the door. But still it is simple, but it has a high gripper motion range, and also the force application is not optimized because it is applied in the center of the basket. And also the angle is not good because it's not vertical, so it's not optimized. And also the force is transmitted through the door, which is a high load on the door. So we move to the next conceptual design. That this time the force is applied in the back of the basket, and also the handle is mounted in the back. Now the force is optimized, but as you can see, the mechanism is relatively complex, and also there is still a non-linear movement for the trajectory for the gripper in order to perform the unloading process. Then the conceptual design 4 has solved the problem of the gripper motion. That this time we have said there is a very short and linear gripper motion. The good thing is that this mechanism is relatively simple, and also the force application is totally optimized because it is applied in the back of the basket. It is suitable for the heavy load, and also the force is applied vertically. And also the conceptual design 5 is a bit different. That this time we don't have the external basket, the internal basket. We still have the linear and short gripper motion for the gripper, and this time also the force efficiency is high. This is more stable because it has less components. But as you can see, this is relatively complex. So we need to choose one of these ideas to continue the process of mechanical design and development. So we define several criteria that in order to help us to choose one of them, such as vibration compensation, that it should have minimal vibrations, the complexity should be simple, it should have enough volume, the base should be it should be lightweight, it should be robust against the external forces and the damage in the rear board. It should be easy to manufacture, the appearance should be nice, force efficiency is important as I mentioned. The gripper motion range, as I said, it should be short, and also the gripper motion type, we prefer to be linear rather than round. Therefore, we designed this table with the subjective scores for each criteria, and here you can see 5 designs. And we assign the weights and everything, and finally we can see that the design number 4 with the highest score is choose to be developed for the next steps. So for the selected mechanism, we started the mechanical design for it, but there are some challenges and considerations that I want to mention. For instance, as you can see in the first video, the leg robot while moving it may crash or fall over. That's why the design should be robust enough against the impact forces. As you can see in the second video, for instance, the robot while moving, it generates a lot of vibrations. So the design should be robust against the vibrations. It should be easy to assemble and disassemble because it's going to be attached and disattached in the operational area. The volume should be optimized, it should be lightweight, and also it should be cheap to manufacture. Therefore, the design step started by defining different revisions. From the beginning, for instance, the first one just shows the mechanism functionality, and then some features added, the geometry of the handle has been changed, the handle link has been completed, several features have been added, like the centering guides for the basket while on is performing. And also from revision 4 to revision 6, you can see several modifications. This phase was the main phase of project that took about 6 months. For instance, here you can see that the joint limit has been designed in order to limit the range of the motion for the handle. The mount design has been completed. The grips has been added to the external body to make it more robust. And also, another stuff you can use has been added to the design. Furthermore, some simulations and analysis has been done on this model. For instance, in the rigid body dynamic simulations, you can see here that the input of the simulation is the displacement of the link, and the output is the amount of the force applied on each joint over the time. And here in this one, you can see the maximum applied force on each joint. Final element simulations also has been done. For instance, the first one, you can see that the stress applied on the mount by displacement in the component has been analyzed. For the second one, for instance, the operation of opening and closing of the battery case has been investigated by using these simulations. And also collision coherence analysis has been done in order to make sure that there is no collision between the internal parts of the mechanism while the unloading process is performed. Therefore, the final design, as you can see here, here you can see all the joints in both configuration of the closed and open mechanism. That we have 6 joints that 4 of them are rotational, 1 is linear, and 1 is contracture. And here you can see the final render of the design, and here is the picture from my physics lab. You can see the expanded view of main components in the container mechanism. As I mentioned, the operational overview is like that the arc rods grasp the trash, drop it inside the container, and then grasp the handle and pull it up by about 11 centimeter, and then the unloading process is done by rotating both the basket and the door at the same time. Then this design has been manufactured with ABS material, and then also SLS manufacturing method has been selected for 3D printing. The part has been presented in the mechanical workshop of IIT, and after the printing, additional finishing has been done on the parts in order to minimize the friction in the joints. Here I would like to mention some of the features of the mechanism. Firstly, as I said, this mechanism has the feature of autonomous trash unloading without the help of human and without any extra actuator that is done only by the robotic arm. As I mentioned, the robot will fall over. So I have designed some engineered washers that will breathe under a certain amount of the force that is critical. So in terms of the bar movement or impact forces, these washers will be built before in order to prevent damage to the more important and costly parts. For the installation and disattaching the container to the robot, this feature has been considered that you can really fast attach and disattach the container. For instance, you can just need to put the container on the mount and just put it away and just insert the pins. It takes less than 20 seconds maybe. In order to change or disattach the gripper handle, you just need to push two sides of the gripper and remove it. This is very useful for firstly for transportation and secondly because in different applications we are using different grippers, so it should be adaptable with different grippers. In order to make the design robust against the damage and the forces, and also for preventing the deformation after the 3D printing, I have designed this in a way that in terms of the geometry and the ribs, this design is both robust and lightweight. In order to compensate the vibrations while the robot is moving, this feature has been added that there are two magnets considered in this part that attach the internal basket to the external body in order to compensate the vibrations generated by the leg robots. This container is very easy to manufacture and is low cost because first for the desk geometries we are using 3D printing technology, and secondly we are using commercial parts for the joints especially that are available from the local shops. As I mentioned, in order to perform the unloading process, we only require very short and linear trajectory, which makes it very easy for the robotic arm to control it. And also, small errors has been accepted because of this geometry. If the robotic arm has a smaller nose, it still can perform the unloading process. The battery case has been designed in a very user-friendly way. That actually this battery is required for the Nook. And also, we can just remove it without any extra tool, just pushing the two sides and replace the battery. And also, airflow sports has been considered for preventing the overheating of the battery. The interior surface of the basket is totally flat. As you can see, there are 3 joints on each side, but all of the joints are designed in an external way. So there is no hole inside the basket to prevent the trash from getting stuck. And also all the joints are designed in a way to be assembled and disassembled in a very easy and fast way, which is very useful for the future maintenance. And also other features like final element simulation space design, center of mass of the components is trying to be same as the center of the mass of the robot, and also not only in the parts that I mentioned, but also in whole of the design I try to use the minimal amount of the bolts and screws. After that we did some tests. The first test is the integration of the container with the robotic arms. For instance, as you can see here, the arm grabs the trash and drop it inside the container. Here, since we don't have the Z-bar arm yet, we're using Kinoba arm and my colleague is controlling the joystick. And then it is dropped inside the container, and now the robotic arm grabs the handle and pull it up to perform the unloading process. And also, we did another test to mount the container on the leg robot to see if unusual vibrations are generated, but the results were positive and no unusual vibrations has been detected due to the features added. Finally, I would like to present the paper that is published and accepted for the MESA conference that is going to be held in September. And as a conclusion, in this project we designed a mechanism that can have a very significant contribution to the robotics, and also it can extend the capabilities of the leg robots. As you saw, the design started from the sketch and now finished with the physical container mechanism. And we also did all the tests in order to prove that this mechanism can work in real world. Thank you. thank you very much for your attention.
Thank you very much for your presentation. Are there any questions from the board? Yes, please.
Just two comments. Let's say I appreciated your work. I think it's very well done. I saw you considered several criteria to design the basket, and I was wondering whether you also included legal ones, in the sense that legal constraints, in the sense that I believe that these tools need to be safe for the operators who are loading or unloading, and they might have some other requirements. I heard over the radio just a couple of days ago that the ones they installed in Rome have a strange shape because the people need to see what's inside, I guess for legal reasons. So I was wondering whether you took this into account, or how could you possibly change the design?
Actually, for the safety considerations, since all the process is going to be done autonomously without the help of human, so during this process there is no human around the robots, so there is no danger. But for the construction phase, we can consider these things in the mechanical design for sure.
And another small question, I appreciated very much the design of the opening system that was linked to the workspace of the manipulator. Now I was wondering, did you also, at least in simulation, check what happens if this workspace is limited? For instance, if one joint breaks, the workspace will be reduced, and then what happens? Would I still be able to open it, to operate it, or not?
In terms of the breaking of one joint of the arm?
Yeah, for instance, or if the workspace should change for some other external reason, or yeah. I don't know, maybe you buy a different manipulator and it will have a slightly different workspace. What happens? Could you still adapt your design, or?
Yeah, actually, I just tried to design the handle placement in a way that is most closely to the robotic arm. For instance, in some of the conceptual designs, as you saw that it was the handle was mounted in front, and also it was a round shape. So for that one, there is a high possibility that in terms of the breaking of the one joint, it's not possible to perform this operation. But with just having short and linear Gilbert trajectory, I think yes, because imagine that, for instance, there are several ways to perform this simple trajectory for the arm, right? So I tried my best to make the trajectory as simple and short as possible.
I have a couple of questions as well. First of all, thank you for the presentation. It was very interesting, especially to see something completely new emerge from nothing. And the question is this: in the first phase, at some point you gave score to different criteria to pick the best design. So my question is, from a methodological point of view, who gave scores? Because if you give scores, I expect you might give score because you already have in mind one design that you prefer. In this case, you might have a bias. In this case, I should look reasonable to me that you select the criteria, you select the design, and then you give the ask somebody else to give the scores, right? Because they may make a choice different for you. So how it works?
Yeah, actually, we had several meetings and discussions with my supervisors, with my colleagues at ALT. For some of them which are subjective, we decided for appearance. This is something subjective. We cannot do calculations. We did just a scoring by discussion. But for some of them,
so the scores were the output of the discussion. The scores. You didn't have let's say, autonomous raters giving different scores and then see.
No, it was just the meetings and discussions.
The other question is this. I read your thesis, and initially you did the different simulation, whose meaning is not clear of all of them to me, but you did a different simulation to measure different properties. One of them was maybe vibration and so on. When you saw the results with the actual built prototype, you just show that it works. Of course, it may be because of time, of constraints, you have to finish, or because it's not needed. So I would like to understand. I mean, if you had time, I'm just curious. Should you replicate similar tests with the actual prototype, or is it sufficient what you did in simulation? So I didn't see testing simulation in terms of mechanical properties or things like that.
Yeah, even I would like to mention that even after the construction, we did some tests in impact tolerance process. We were hitting very hard into the container, and also we were rotating the robot while the container was mounted on the robot to see when the robot falls down, it doesn't damage. And we even did this test in the real world situation too.
Okay, but will you measure something when you do this test? Because again, it's just it works, it doesn't break. I was wondering because I actually don't know.
Yeah, in real world test, the result is just to see it doesn't break, right? But in the simulations, in the software, no, we have the numeric outputs.
Any other questions? No, thank you again. So next one is